Welcome back from the break. In this session, we are going to be looking on what we call the principles of the galvanometer because our ECG works on the principles of what we call the galvanometer. But before you go to what we call the galvanometer, I want to take you through on what we call the basics of what we call of this diagrammatic illustration. So now we have just brought a very small kind of the tissue from what we call the myocardium. This is going to be tissue A, this is going to be tissue B, and this one is going to be tissue 3. Now, we are connecting electrodes on both sides. Now, what is electrode? Electrode is going to be that electrical device which can be put on the skin and it detects the electrical current generated by the heart. You know, whenever the heart generates electrical activities, this electrical current can move throughout the body, and these kind of electrodes can pick this kind of the current direct from the skin. These electrodes can be a positive electrode and it can be a negative electrode, of which they're going to be having these wires that are going to be taking the kind of the information to this kind of the machine which we call the galvanometer. Okay, so now we want to see how is the galvanometer going to be deflecting if this tissue is stimulated from different areas. Okay, that is going to be the main reason of this session. Let's go ahead and get started. So now let's first pretend for a minute that we are going to be stimulating this kind of the tissue from this area. At this time, it is at rest. And whenever this tissue is at rest, it is going to be electrically negative. Okay, this tissue is going to be electrically negative. All of these cells are going to be electrically negative. Now, if we stimulate this tissue from this area, of course, when the cells become stimulated, sodium is going to start entering into that cell. And if sodium enters that cell, the membrane potential of that cell is going to be changing from resting membrane potential, and it reaches around the threshold. When it reaches around the threshold, voltage gated sodium channels are going to be opening, and a lot of the sodium is going to be rushing in. And this one is going to be leading on that cells to become electrically positive. Okay, so now that one is what we call depolarization. So now this cell here is going to become depolarized, and once it becomes depolarized, through the gap junction, some of the cations are going to be moving to the neighboring kind of the cells, leading to the depolarization also on those cells. So even also these cells are also going to get depolarized. Even also these ones are also going to get depolarized. So now during this kind of depolarization, a lot of electromagnetic force is going to be generated. So now until the whole tissue becomes depolarized. So now the depolarization was moving from the tissue point P up to point Q. Now, the electromagnetic force which was generated here can be illustrated using the vectors. A vector is going to be a one showing the direction of the depolarization or even repolarization. So now, if the depolarization is moving from point P to point Q, our vector is going to be pointing the other side. Okay, this is going to be now our vector. But this vector was for the case of the depolarization, and depolarization is going to be by the movement of what we call the positive charges. Okay, now that we have seen what vector means, let's go ahead and see how is this galvanometer going to be behaving. Okay, where is our pointer going to be deflecting? Is it going to be deflecting to the positive side, or it's going to be deflecting to the negative side? So now this side here is going to be now for example our positive side, and then this side here is going to be now our negative side. Now, what does the principle of the galvanometer say? If the depolarization is moving from the negative electrode and it is moving towards a positive electrode, our pointer is going to be moving towards the positive side. Okay, so now our pointer is going to be now moving to to the positive side, and this one is going to be giving us a positive deflection. Okay, so now how does the ECG give us a positive deflection? This one here is going to be our positive deflection. Okay, so now this one is what we call a positive. This is what we call a positive deflection. Okay, this is what we call a positive deflection. Now, it means a positive deflection is going to be moving up. Now, whenever the whole of this tissue becomes fully depolarized, shall we again have electromagnetic force being generated? No, it means that's the only time when our pointer is going to be coming back to the neutral. Okay, and it's going to be producing an isoelectric line. An isoelectric line is going to be this line which is going to be moving, showing that either the whole tissue is fully depolarized or even the electrical current is being held somewhere within what we call the myocardium. So now that was for the case of experiment on tissue A. When we come on experiment with the tissue B, the other tissue, we stimulated it from this side. Now, this time around, you're going to be stimulating it from the other opposite side, the Q side. Now, this tissue at this time is still at rest, okay? And whenever it is at rest, it is going to be electrically negative intracellularly. Now, if we stimulate this kind of the tissue from this side, sodium is going to start entering these cells. And when the sodium enters these cells, the membrane potential is going to be moving and moving until it reaches what you call threshold. When it reaches threshold, voltage-gated sodium channels are going to be opening and a lot of the sodium is going to rush in. And when sodium rushes in, the electronegativity of the cell is going to be washed away. And we say that these cells is becoming depolarized. Okay? So now this time around, the depolarization is going to be coming from these cells. Of course, the depolarization of these cells will lead the depolarization of the neighboring cells. So even these cells also becomes depolarized. So now the depolarization is now going to be moving throughout the entire kind of the tissue. Now, you realize that now the depolarization is moving from point Q going to point P. So now, how is it going to be now our vector? Now, our vector is going to be facing this side. Okay, our vector is going to be facing this side, and still our vector is going to be still carrying a positive charge because the depolarization is starting from point Q coming back to what we call to point P. Now, what does the principle of the galvanometer say? Whenever the depolarization is moving away from the positive electrode towards a negative electrode, our pointer is going to be moving to the negative side. Okay, so now this one is going to be our negative side, and then the other side is going to be now our positive side. Now our pointer is going to be moving towards a negative side. So now this one will give us a negative deflection. So now how does the ECG represent a negative deflection? This one here is going to be a negative. This one here is going to be a negative. It's going to be a negative deflection. So now this one on the ECG, whenever you see a downward deflection, it represents a negative. It represents a negative deflection. Okay, it represents a negative deflection. Okay. Now we are going to be now repeating an experiment with this kind of the tissue, which is going to be a bit slightly thicker. Okay, this tissue is going to be slightly a bit thicker. It is too big compared to this tissue B and then tissue A. We want to see how is it going to be different in terms of what we call vector formation. Now, this tissue is going to be, for example, at rest. And whenever this tissue is at rest, it is going to be, the cells are going to be electrically negative. Okay? Now, let us pretend for a minute and we are going to be stimulating this tissue from this side. If you stimulate the whole of this tissue, these cells are going to start now accumulating a lot of the sodium. And once they accumulate a lot of the sodium, the resting membrane potential will move to the threshold. Once it reaches the threshold, voltage-gated sodium channels are going to be opening and a lot of the sodium will rush in, okay, and will make the electronegativity of the cells to be washed away. And these cells are going to become depolarized. And once they become depolarized, now the depolarization is going to be starting from this side, moving to the other side. Okay, so now we are saying that the depolarization is moving from the negative electrode going to what we call to the positive. Going to what we call to the positive electrode. Now, when you look on the depolarization of this tissue and the depolarization of this tissue, you realize that here we are going to be having a depolarization which is going to be a bit of a bigger magnitude. Okay, the depolarization generated on this tissue is going to be of a bigger magnitude compared to the tissue B and then compared to tissue A. What does this one mean? It means even the vector which is going to be created, is going to be of bigger amplitude. Okay, so now a vector is going to be of bigger amplitude. Okay, and this depolarization and this vector is going to be carrying what we call the depolarization, which is the flow of the positive charge. Now, if we bring in the rules of what we call the galvanometer, whenever the positive charges or the depolarization moves away from the negative electrode towards a positive electrode. We said that one is going to be giving us a positive deflection. But this time around, the positive deflection is going to be having an extensive, big kind of the amplitude compared to the experiment of the tissue A and then what you call tissue B. What do I mean by this? This is going to be now the size of the amplitude of this positive deflection. It's going to be giving us this kind of deflection. Now, when you see this deflection, this positive deflection, and this kind of positive deflection, you realize there are going to be a difference. And the difference in this one is going to be as a result of what we call the thickness of the myocardium. If the myocardium becomes thick, even is going to be giving us a lot of the repolarization, which will give us a bigger vector, which will also give us a strong kind of the positive or the negative deflections. Okay, so now that one also makes a lot of sense. Now, if this tissue becomes fully depolarized, there is not going to be any kind of electromagnetic force which is going to be generated if it is fully depolarized. For that reason, it's going to be the pointer is going to be now coming back to what we call the neutral position. And whenever the pointer moves back to the neutral position, this one gives us what we call an isoelectric line. Okay? And even also, whenever the electrical impulses are moving perpendicular, okay, whenever they are moving perpendicular on this kind of this tissue, also that one, the pointer is going to be also moving back to the neutral, which will also give what we call an isoelectric line. And even again, another reason why we may even have what we call isoelectric line is like, for example, on AV node. The AV node also holds the action potentials for approximately 0.1 second. That one also can also produce us what we call an isoelectric line. Okay. So now, the whole of this kind of the myocardium is fully depolarized. So now let's now first pretend that now it's time to repolarize. Now, how is repolarization going to be happening? First of all, repolarization means the cells are going to be now allowing the out movement of what we call the potassium. We are going to be having efflux of what we call potassium whenever the cell is becoming repolarized. So now let's first pretend for a minute that this kind of the tissue is going to be getting repolarized from this side. Okay, it's going to be getting repolarized from this side, going this side. And we have said that whenever this tissue is getting repolarized, it means it's going to be now starting to regain its electrical negativity just because of the exit of what we call the potassium. So now the electrical positivity is going to be getting lost as these cells are going to be becoming electrically negative. Okay. So now they are regaining what we call its electrical negativity. So now, when this tissue regains its electrical negativity, we say this tissue is getting repolarized. But the repolarization was moving from this side going this side. It means even also the vector which is going to be created is going to be facing this side. Okay, it's going to be facing this side. But this time around, this vector which is created is going to be as a result of what we call repolarization. Now, whenever the negative charges are moving away from the positive electrode towards a negative electrode, the principle of the galvanometer says that one also gives us what we call a positive deflection. Okay, whenever negative ions are moving towards a negative electrode, it gives us a positive deflection. And even also, whenever positive charges are moving towards a positive electrode, it also gives us a positive deflection. That is according to the principles of the galvanometer. Okay, we're going to just have a very quick break. Immediately after the break, we shall go through what we call the leads, because the ECG has 12 leads. Let's meet immediately after the break.